To show you that there's been quite some activity in the southern hemisphere. We're a relatively small group, but we've been very active, I think. So I'm going to talk about YOPP-SH. That's the acronym that we use, what we've been able to achieve so far, and implicitly what our future plans are. So I'm going to have some pictures that we've gotten from the different stations of balloon launches, and this is from Davis Station in East Antarctica. So we've had tremendous contributions from the international community, so we've tried to encourage, pictures and videos as a record of everybody's contribution here. So it's really a community effort. Okay, so a brief outline. We'll have some introductory remarks, show you what we were able to achieve in the summer special observing period as sort of background for where we're going right now, show you some results, so some science, and then the winter special observing period, which is just about ended, and more organisational aspects there, okay, and more pictures of balloon releases from different stations. Okay, well, you know everything about the WMO Polar Prediction Project. It's been going on for 10 years, as you know, and it's just about coming to an end. The goal, of course, is improved environmental prediction, and it's for the polar regions, so both north and south. You know about the focus time period of the year of polar prediction. It definitely wasn't a year, and it's because we've got two hemispheres. The southern hemisphere component of this, YOPP-SH, started later. It actually started in a YOPP meeting at WMO headquarters in Geneva. And at that time we realised that there wasn't much activity in the southern hemisphere. There's a large contingent of nations and people interested in the north, but we needed an organising activity in the south. Our focus is the same as in the north, so I'm going to talk about the summer special observing period, which ran from November 2018 to the middle of February 2019. Mostly additional radiosonde observations. We had some additional drifting buoys in the Southern Ocean, a few additional automatic weather stations on Antarctica, and definitely some additional ship observations. Okay, so this is kind of an important plot here as to how we're going in the forecasting skill. Now this comes from Peter Bauer at ECMWF, and if I say anything incorrect, I'm sure if he's still here he can correct me. This is a measure of the forecast skill, the anomaly correlation coefficient at 500 HPA, so that's the middle troposphere. It's in the 12-month running mean. The different colours are for 3 days into the future, 5 days into the future, 7 in green, and 10 days in yellow. And as I understand, probably it's different today, but 60% was, quote, termed useful. So there may be some forecast skill for both polar regions at forecast day 7. And we've seen that with individual events in the Antarctic. So I'll focus primarily on plus 3 days. And on this vertical scale, if you're at 100%, that's perfect prediction, probably on the synoptic scale. So the heavy blue lines are for the regions poled of 60 degrees north, and the thin blue line on the bottom, on the other side of the yellow, the blue shading, is for 60 degrees south and poleward. So the skill obviously is actually exceptional even today, at 3 days, and then it falls off quite dramatically after that. So one of the conclusions here is that when I was started off, and I worked for the Australian Weather Bureau as a forecaster for a little while, realised that I was much better suited in life as an academic, that the forecasting skill in the southern hemisphere was substantially poorer than in the north. And you can see that in this plot by this big gap between the two time series, right? And there's a major convergence, although not completely, around the late 1990s. And that's when the assimilation of the microwave radiances started. So a lot of this in the southern hemisphere has been the exceptional improvement in how to use the information from space. And that's because we've got this big data sparse ocean surrounding Antarctica to the north. The Antarctic does lag behind the Arctic. There are many good reasons why. And I think the goal of YOPP-SH, if we can do it, would be to close that gap, and even in the ideal world to exceed that. Okay, so I'll show you a little bit of results from the summer special observing period. And we did collect observations for the 3 months from stations around Antarctica. I'm going to focus on a period in the middle of, from the beginning to the middle of January, when there was most of the observations collected. And these are data denial experiments, another phrase that's used to mean the same thing as observing system experiments. We're using the framework of the Antarctic Mesoscale Prediction System, which is run at NCAR. And its goal, primary goal, is to get the aircraft that fly out of Christchurch in New Zealand due south and land at McMurdo. And so there's nowhere else to go. There's not alternate runways as there are with almost any other airport in the world. So there's this phenomenon, they fly out to a certain latitude where they've got enough fuel to go home. It's called the point of safe return. And then once they commit beyond that, they have to land. So the weather is a very, very important part of this. And as you know, there's lots and lots of flights, both from New Zealand into Antarctica and within Antarctica, particularly to the geographic South Pole. So we're using domain 1, which is 24 kilometres, domain 2, which is a nested domain at 8 kilometres. There's much finer domain inside that when it's run routinely. Okay, so I'm going to show you some results of these observing system experiments, data denial experiments. Okay, so colours are a little bit washed out on the screen. The plots are on the top row are for temperature, so the forecast temperature, the wind speed in the middle, and the relative humidity, so basic meteorological variables. And it's divided between south of 60 degrees, that's where most of the observations were taken, and then north of 60, and there was almost nothing in addition except for Macquarie Island. And this is, we're comparing the forecasts with the ERA 5 global reanalysis, which we're taking to be truth. Not that I believe it's truth, but it's probably the best approximation we have, at least for the large-scale variables. So this is arranged so that when we use the additional radiosondes, when their error is smaller than when we don't use them, it shows up as red in these plots, okay? And the forecast error reduction is substantial. You know, the brightest reds here are the order of 10% in the mean absolute error. So that is a dramatic improvement. And so focusing primarily south of 60, this is plotted versus pressure from the surface pressure of around 1,000 millibars to 20 millibars, or HPA, in the stratosphere, and it goes out in forecast time to 3 days. So the temperature south of 60 is very well forecast. When you add these additional radiosondes, they go, the impact lasts throughout the 72 hours. There's some improvement also at the tropopause level, around 300 to 400 millibars, and in the upper troposphere. The wind speed is quite different because of the horizontal temperature gradients in the atmosphere. So if you know about the concept, which many of us do, about the thermal wind, so if the horizontal temperature gradients are forecast better, then the upper level winds, that's the jet stream and on into the stratosphere, are better captured. And rather than the impact happening right away, it happens later. So that's around 2 days. The relative humidity is better forecast out at about 2 days also. And that is a less constrained variable than the temperatures and winds, which are coupled dynamically together. North of 60, there is a response. It's a few percent in the temperature, wind speed, and relative humidity out at 2 days approximately. Okay, so I wanted to show you a little bit about how this evolves in latitude. So this is the same plot for temperature for every 10 degrees latitude. The important thing to realize is that we've cut out everywhere that's below the ice sheet surface. So in 80 to 90 degrees south, if you know anything about the geography, there's the huge Antarctic ice sheet sitting there. So mostly that's all above, 700, 600 millibars. So mostly the low-level part of that is over the 2 ice shelves, actually. But by the time you get to 60 to 70 degrees north, you're mostly out over the ocean and where we haven't collected additional observations. And you can see, as far as the temperature goes, there's a significant improvement. And then the impact is still there, reduced, and it dies away as you go farther north. Okay, this was a case study that was a fairly intense low. This thing was around, this is in the middle of the summer, and it got down to around 960 HPA. So if you saw that in the North Atlantic in the middle of summer, I think you'd be greatly worried. It's fairly reasonably common these days around Antarctica as the southern annular mode has strengthened in the summer. On the left-hand side is when we use the additional radiosondes, and on the right-hand side, when we don't, we take the difference with ERA 5 as far as the mean sea level pressure goes, and you can qualitatively see the same pattern. The amplitudes are significantly bigger when you don't have the additional radiosondes. We were fortunate to have an automatic weather station, Austin site, which had just been serviced, so it was fully functional, and it was just a little bit offshore, a little bit away from the centre of action, onshore, of course. So let's see. I can just say that the time series of the station pressure, the 2-metre air temperature, and the winds were pretty well forecast, better by when we added the additional radiosonde observations. Perhaps what I'll do is I'll highlight the wind speed. And it doesn't matter whether you have the observations, which are in the black, or the green, it's a little hard to see on the screen, which was the ERA 5 global reanalysis, or the 2 forecasts. You got 4 days of very accurate forecasts. So it is quite possible to do well under the right circumstances. Okay, so we had some nice efforts in education and outreach by our colleagues from Italy, and this was a educational activity both in Milan and in Antarctica, and interaction between the two. So let's go on. And I'm just highlighting some of the associated activities. This was a survey that was conducted on the usefulness of weather observations, and there was a wide variety of questions answered based on, and this was work from Vicky Heinrich at the University of Tasmania. She'll probably be, I believe she'll be talking about this later. And what was the most useful information that the users, so these were people who visited Antarctica or the Southern Ocean Islands, and it was the wind. And it was interesting when I heard the discussion about the Arctic, it's the same story. So there's a lot of commonalities between both parts of both poles, even though they're quite different geographically. All right. So let's talk about the winter spatial observing period. This ran on from the middle of April to the end of August. We used this targeted observing period approach that we first learned about from our colleagues in the Arctic, and that was a period of enhanced observations. Primarily, we organised additional radiosonde descents, and just on the right, you can see all the different stations, not the, I should say, Gough Island, Marion, and Agulhas didn't end up being part of this, but there's about 24 additional stations. Some went from 2 to 4 soundings a day, particularly the cities in southern Australia. So this was a substantial enhancement of at least the radiosonde observations. There was 2 targeted regions to make this more tractable. This was basically East Antarctica to the Ross Sea and what I would call the Greater Antarctic Peninsula. Kinds of things we're looking at is the major coastal cyclones, atmospheric rivers, which are a favoured topic these days from many people, these concentrated poleward moisture transport regions, and cloud impacts. By that I mean the mixed phase clouds in particular. We're also looking at as you might have guessed, the impact of the additional radiosonde observations. Can we improve the forecasts in the conditions of the real observing system where there's tons and tons of data coming in from space? And we're particularly interested in prediction of the extreme events, which is so important for operations and safety. There are enhanced measurements going on, particularly focused on clouds in the Antarctic Peninsula and this was a table put together by Penny Rowe, and these are for Escudero Station on King George Island, Rothera, which is the British station on the west side of the peninsula, and Marambio, which is an Argentinian station around just east of the tip of the peninsula. A lot of surface radiation measurements, which give us indirect information about the clouds. So these things are good for investigations of, once again, atmospheric rivers, extreme precipitation, which are tied to these rivers, foam warming, which is descent on the lee side of mountains like the Antarctic Peninsula, and major melting events. So Irina can testify to all of that. We also had some fairly extensive measurements at Davis Station in East Antarctica. There was a VHF clear air wind profiling radar. So this thing provides horizontal and vertical winds from 1,500 metres to the lower stratosphere, and it's essentially continuous. So one way you can make up for the data sparsity is to increase the coverage in time. And so this would be a good kind of look forward to the days when we have perhaps less radiosonde observations as can we make better use of some of these remote sensing instruments. Also, a micro-rain radar, which gives vertical profiles of radar reflectivity, and from that you can infer precipitation, reflectivity, vertical motion, and precipitation rate. Okay. There's been some effort by a number of stations, and they're shown here particularly in the peninsula, but also Terra Nova Bay, that's Janbogo, the Korean station, and Dome Concordia in the high interior. And these are additional sensor packages that you put on for the radiosondes. You've got the original radiosondes, and then you've got these Hemisphere sondes, and they're vibrating wires, as I understand, and the deposition of ice on the vibrating wire changes the frequency, and then you can infer the cloud liquid water and the cloud ice, which are key forecast variables that none of us do very well. Okay, SIP South. Francois Massenet talked about this already, but I just wanted to say that this does come under the umbrella of YOPP-SH, and this was an exercise, contributions, figuring out how well we can forecast the minimum of the sea ice extent around Antarctica. That's a very weak metric. You'd want to look at particular regions, even particular places. This is just the broad scale. You can see from the diagram here that there's quite a scatter. Most of that is attributable to the coupled ice, ocean, sometimes atmosphere models that have some significant issues. And right now, this has been going on for several years, and they're going to look at the sea ice growth period during the winter special observing period. Everybody likes atmospheric rivers. They're a big deal in California. So this scale was put together by our colleagues at the Centre for Western Weather and Water Extremes. Okay. So on the left, this is from the GFS Global Prediction. What is the maximum scale of the rivers that could be expected over the next 7 days? And they use the ensemble results as well. And then these animations of the integrated integrated vapor transport on the right, and there was a nice animation for that. So that was a nice tool in planning for our targeted observing periods. Okay, so the targeted observing periods, we had 7 of them. The last one has just finished. It's about 4 of them were Antarctic-wide, and 3 of them were regional. Okay, so some pictures. Okay, you notice the Aurora Australis from Showa Station. Below that is from McMurdo. The bottom is from the German Neumayer Station. And let's see, I forget who is in the bottom left. I think Eric will tell us about that. Okay, we had a forecast the TOPs. We only had a limited number of radiosondes. We had a limited number of people. We're asking everybody to volunteer. They're getting up at all sorts of strange times of the day and night to do this. So the forecasts were we had forecasting teams for both regions that I talked about. This was an example of a forecast product that we had put together by Art Kayat of the US program. And so he thought 5 days was a good time horizon. He had his traffic lights views for key stations, and this was a go for Antarctic-wide. And once again, we made extensive use of windy.com. Okay, Okay, so to summarise then, the summer special observing period was a big success. Results show that the forecasts over Antarctica have been significantly improved with the additional radiosonde ascents, especially from the Antarctic interior. There really has been tremendous. This has been an international effort, and great contributions. And we did make a real effort to increase the radiosonde coverage from north of 60 so we could better capture the oceanic cyclones coming in from mid-latitudes. Okay, thank you.
Thanks very much, David. And I think on behalf of everybody, I think I'd like to say a sincere thank you to you for all the leadership you've put into making sure that there is a really strong focus on the Southern Hemisphere in the project. So thank you.
Thank you.
Yeah, please. It's good to see that Thomas is awake. I've got a question here from Thomas, which is more about the predictability in the Southern Hemisphere. He's suggesting that perhaps part of the reason for the gap between Northern and Southern Hemisphere in the European Centre verifications is because the Northern Hemisphere has more predictable long waves, medium waves, to do with the orography really and land sea, than in the Southern Hemisphere, where that's part of the reason. It's a dynamic question.
I'm not sure. So there was this tremendous warming event that took place in March of this year at Dome Concordia. Basically, they had summer in basically the middle of winter. And so we looked at that as a kind of a learning experience. And that was forecast pretty well 7 days out. Okay. So yes, you would expect the long waves, better defined in the Northern Hemisphere. I don't know. And of course, it depends on which year you're in too, right? They're all very different from each other.
Anyway, questions from the floor? Yeah.
When I looked at the maps of Antarctica, the West Antarctica had less coverage in terms of stations between the peninsula and the Ross Ice Shelf. Is that kind of a blind spot, and is that important regarding the future of the West Antarctic Ice Shield?
Yeah, that's an unfortunate reality. There's a term that got formulated for the weather in that region. It's called the polar variability. So that's the most challenging. There's the largest interannual variability there because of the tropical forcing is so marked in that region. And yes, there's basically nothing as far as conventional observations, at least in the upper air from South Pole to Easter Island, which is around 30 south. So it's this giant data void. And so yes, when one doing predictions, for example, for the peninsula, which is, south of South America, you've got nothing but ocean. So you really need to make sure you're doing your best possible job with the satellite radiances, for example.
Yeah, there's a quick question here from Helga. Hello, Helga. He's really following up on what Thomas was saying about whether idealised predictability studies could help. So, yeah. Any other questions from the floor? Time for one more question? Yep. Please go to the microphone over there.
Just to add to the comment of, we consider West Antarctica as a place where it's very difficult to operate. The big gap there is because it's very difficult to reach the coast to make any operation. I remember, I have an anecdote, Koreans, when they like to establish Jumbo Go, they like to use at first sight the west part, the ovest of the Ross Sea. And when I listen, I say, oh, why? Oh, there is no station there. I say, there is a reason. And they place Jumbo Go near to our station. It's impossible to operate continuously. We need new technology in this respect, if you like to fill this gap. That is very important.
The Russians had a station, Ruskaya, and it was the most extreme place you could ever imagine. And furthermore, they had a ship that was moored there in the wintertime. And like these historic ships, it broke out and drifted out into the Southern Ocean. So it's a wild, wild coast. So, yeah.
Thank you. I'm going to just take one more question from Thomas, which is a very good question, and put it to you. And that is based on the results from the SOPs, which it's small, a few percent, but do indicate there is improved accuracy from increased radiosondes. Do you think that's likely to lead to actually increased radiosondes generally rather than just for SOPs?
Well, yes. So what are the issues with radiosondes? Well, you need to spend the money on the gas, which is expensive if you're trying to use helium. You've got to have the people to launch it, right?
Cost benefit.
Yeah, it's cost benefit. I think that we haven't done the studies to identify what are the likely places that are of most benefit, but we know we've got 2 interior sites at South Pole and Dome Concordia. So that might be the investment that's tractable.
Cost benefit there is worth it, perhaps. Yeah.
Probably.
Okay, thank you very much again, David.
Yes.
Thank you, David. And I will introduce our next speaker of this